Well, let's start today with buffers. We talked about what buffers are. So when we are saying buffers, what we are solution, we are meaning the as soon as we say buffer solution, we understand in the back of our mind that what it is this solution doing, it is resisting the change of pH. Why is it important? It is important for several reasons. One of the most important reasons that affects you and me and everyone, every living being in Earth, is the blood. If the blood is having for a long period of time a pH that is less than 7.1 or more than 7.4, then it's very dangerous for your health and it is risking a lot. Okay. What buffer is doing, buffer solution is doing, is that even though that you are adding an acid or a base in that solution, what you are doing, you are preventing the auto-ionization of water to take the power of either hydronium or the hydroxide. Remember what we said in terms of the auto-ionization of water. Water liquid, it in equilibrium is forming hydronium and hydroxide. Okay. Now, what if this is increased when we are in a neutral situation? Then it's fine. Whatever is the concentration of hydronium is the concentration of hydroxide. Therefore, we are on that we know as a neutral solution. But if for some reasons you are increasing the concentration of hydronium, then what you are doing is we are making the solution acidic. And then if you are saying that, well, okay, no, I will add some base there, some quantities, some compounds that will make it more, will add more hydroxide. And by doing so, what you are doing, you are making the basic solution. You are making the solution more basic. So buffer solution, what it is doing is protecting, quote unquote, water to uh, through the auto-ionization to become acidic or basic solution. Okay. Now let's see how is a buffer is formed. So now we know what is a buffer that is resisting the pH. And even though that when we are adding either an acid or a base, a good a good idea as to what buffer is let's suppose that you have here a bucket, a solution in which you have the uh, weak acid or an acid, and I will just draw three. So an acid, and you have the ion part of this acid. Let's suppose now that what you are doing is you are adding an H plus. Adding an H plus into this, in some ways, into this solution, what will happen is that this will go uh, to bond with A minus, and then as a result of this, an HA is formed. And then you are adding more, but the pH will not change because as a result of the equilibrium, this AH will be again uh, uh, broken down into H plus and A minus because we are on the equilibrium situation. But then when all of those A minuses are taken out from H pluses.
Issues in Indigenous Canadian society.
One more H plus added will change it and become it acidic. Up to the part when we have those 3 H pluses that are added, the pH is not changing. But as soon as we are adding the fourth one, then the whole solution is becoming acidic. So this is a buffer solution because it is resisting the change of the pH in the solution, even though that it seems that we are adding H plus or hydronium. Okay, so now let's see how is a buffer solution formed, because there are different ways that we can form a buffer solution. Okay, so the very first way or first method on forming a buffer solution is when we combine the weak acid with its conjugated base at a ratio 1:1. Remember what we said as a weak acid is. It is on pages 8 and 7 along with indicators. So if we are combining a weak acid, HA, with its conjugated base, then what it is happening, what we are doing is we are forming a buffer solution. Now, keep in mind that when we are saying add the conjugated base, we cannot just go and add A minus there, okay? We don't have that ability to add A minus, but what we do is we add a salt that is has a high solubility, that has, as a part of the compound, it has group 1 elements and that ionic part of the conjugated base. What do I mean by this? Let's suppose that we are taking HF, which is one of the most common weak acids that we have in that we are using, and it is in your data booklet on page 8 and 9. It is the hydrofluoric acid, and then its conjugated base of the hydrofluoric acid is F minus. But we don't have that ability to have in a bucket a bunch of H minuses. Therefore, what do we do to form a buffer solution? We say that we are adding the hydrofluoric acid with a salt that is formed as a result of the conjugated base and a group 1 of the elements. And the group 1 are elements that you can see them in your data booklet as well, are lithium, sodium, potassium, rubidium, and so on. So a very common one is sodium fluoride. Why are we doing this? Remember that we have them into an aqueous solution, and since the salt that is like sodium fluoride, like this, it is broken down into sodium plus and F minus. Therefore, what we have in that buffer solution is this as the acid, weak acid, and those ion, the conjugated base of the same acid, but now we have introduced it into the solution through a salt. And the ratio between the salt and the weak acid has to be 1:1. let's take a look now why it is important that beside the fact that we are dealing with a weak acid and its conjugated base, okay, why is it important that the ratio between the two, the weak acid and the conjugated base, to be 1:1? So let's suppose that we are having weak acid as HF in aqueous solution plus sodium fluoride in aqueous solution. What is the reaction that is going to happen here on this case? What are the products that are formed on this situation? So now if you have, let's say, the ratio between HF and NiF is 1:1. So if you have, let's say, 5 moles of HF, then being in a ratio 1:1, you will have 5 moles of NHF. And then in this case, they are both limiting reagent, so they will both be having the same change because it is the same number of moles. So if this is initial and this is change and this is the equilibrium, the change will be 5 moles will be used, 5 moles will be used, then we'll have 5 moles here that are produced and 5 moles here that are produced. So at the equilibrium, we'll have 0, 0, and then here we'll have 5 moles, not plus, but just 5 moles because it's at the equilibrium, and 5 moles here. Now, those two do not affect the pH of the reaction at all. And what we have here is 0. So what possibly affects the pH of the solution, it is inexisting, meaning that the pH of the solution will be resistant to the change. Okay, well, this is why we have a buffer solution when we have a weak acid and its conjugated base, but they are at the ratio 1:1. Okay. Now, the second method in which we are able to form buffer solution is when we are having a weak acid and a strong base. But the ratio that we have here is 2:1. And we'll see why it is 2:1. Weak acid is the case when we have, let's say, let's stick with hydrofluoric acid. And a strong base, the most common strong base that we have seen since we have started chemistry is sodium hydroxide. Okay, so this combination, when it is at a ratio 2:1, it's able to form a buffer solution. So now, why is it important? Because what we want to see in the solution that is forming a buffer, we want to see almost the same concentration or the same number of moles of the weak acid and the same number of moles of the conjugated base of it. So the basic of the basics of the buffer solution is when we have the weak acid and its conjugated base at the same or roughly the same concentration. Let's see what is happening on the case when we have HF and NOH. So the reaction will be something like this: plus NOH. And since we are dealing with a base that is completely dissociated, then we will have, as a product here, we'll have water and which is a salt. because you know that even from, I don't know, chemistry 10, that when an acid and a base is formed, water and the salt is formed. Okay, good. We're good. Are we good up to this point? Now, why is it at a ratio 2:1? Okay, let's suppose that we are starting with 10 moles initially. We are starting with 10 moles of hydrofluoric acid. And then if we have the ratio 2:1, and on the coefficients here, the ratios of hydrofluoric acid and sodium hydroxide is 1:1. What do you think that the 2:1 will represent in terms of number of moles for sodium hydroxide? 10 or 5 or 20? So the 2:1 ratio for the weak acid and strong base, when we have 10 moles of the weak acid, will be expressed as having 10 moles of sodium hydroxide. And initially we have 0 and 0 here. And now the change that is happening, which one is the limiting region here? Is the hydrofluoric acid or is the sodium hydroxide? Since the ratio is 1:1, what is the limiting region in the sense as which one is finishing first, hydrofluoric acid or sodium hydroxide? It is sodium hydroxide. And since it is a strong base, will be completely, quote unquote, eaten up by the reaction, completely taking part on the reaction. So 5 moles of sodium hydroxide will participate in the reaction. Since we are on the same side of the reaction, 5 moles of hydrofluoric acid will react as well. When we are changing the sides of the reaction, we will have 5 moles of water produced and 5 moles of sodium fluoride. Are we good with this part here? Because there is a difference. What we have seen and what we have done at the ice table, it's the concentration. And now we are looking at moles, but we are using the same principles of the same idea as the ice table is. Does it make sense, guys? Okay, so now at the equilibrium, what we have is we have 5 moles of hydrofluoric acid, 0 moles of the strong base, sodium hydroxide. We have 5 moles of water, which we are not even interested on it because we do not, this doesn't even affect anything into the equilibrium in terms of the calculation, doesn't affect the value of Ka or anything like that. And we have 5 moles of sodium fluoride. However, sodium fluoride is not staying as sodium fluoride. Sodium fluoride is broken up into sodium ion and fluoride ion in aqueous solution. So then, see what we have now at the equilibrium. We have 5 moles of hydrofluoric acid, and we have 5 moles of its conjugated base. Therefore, we are on the conditions that this solution, when we have a weak acid and a strong base at a ratio 2:1, it's forming a buffer solution. The third method, you would guess now what it is. The third method to form a buffer solution will be when we are combining a weak base and a strong acid. So weak base and a strong acid. And again, the ratio is 2:1. Okay, The example of a weak base is when we have, let's say, uh, sodium fluoride. Why sodium fluoride in aqua solution? Because this will be broken down into sodium ion and fluoride ion. And what we have for fluoride in our data booklet, it is a conjugated base, and it is a weak one. Plus a strong acid. What is a strong acid? Let's say, I don't know, hydrochloric acid. The reaction that is happening here, and it is a complete reaction, is that it is forming sodium chloride in aqua solution, which will be broken down into sodium and chloride ion, and hydrofluoric acid in aqua solution. Now let's take a look as why do we have 2p on a ratio 2:1. Okay, so I will rewrite the reaction again here, and I will not just state the state of matter, but you know now that what we are dealing with. Okay, and then we said that it has to be 2:1. So now let's pick some other numbers so that we know the ratio 2:1. Let's suppose that we will have, let's say, 3.2, to make it weird, 3.2 moles of sodium fluoride salt. Since we are looking for 2:1 ratio, and the ratios in the balanced reaction are 1:1, what do you think that the number of moles for the hydrofluoric acid will be? Will be 3.2? Will be 6.4? Or will be whatever is half, 1.6? I think 3.2 divided by 2. Yeah, 1.6 will be 1.6 because it is half of what we have in the weak base. So will be 1.6 moles. Initially, we have 0, 0 here. So this is the initial, but keep in mind here, we are working with the moles because when we see the reaction, we refer to the balanced reaction and to the ratio that the number of moles have. Okay, now the change. Which one is the limiting region here? Is sodium fluoride or is the hydrofluoric acid? Hydrochloric acid, sorry. Is the hydrochloric acid. And being a strong acid, will be completely used up in the reaction. So the change is a negative 1.6 moles. Since we are on the same side of the reaction, even for sodium fluoride, we will have a change, a negative change of 1.6 moles because the ratio is 1:1. Since we are changing the side of the reaction, we are moving on the other side of the reaction, then the change of sodium chloride is positive 1.6 moles, and the change of hydrofluoric acid is 1.6 moles. So at the equilibrium, what we have is we have a 1.6 moles for sodium fluoride. We have 0 for hydrochloric acid. We have 1.6 moles for sodium chloride. So this is sodium fluoride. This is sodium fluoride, and this is sodium chloride. And we have 1.6 moles of the weak acid. So since sodium chloride is a neutral salt, meaning that does nothing to pH of the solution, then we will end up having 1.6 moles of sodium fluoride and 1.6 moles of hydrofluoric acid. Now, sodium fluoride, on the other hand, it is broken down into sodium ion and fluoride. So, and this is again 1.6 because it's 1-to-1 ratio. So now that means that we have the acid and its conjugated base at the same ratio 1-to-1 or very close to 1-to-1. So this is those are the three methods that the weak acids, sorry, the buffer solutions are formed. So weak acids and its conjugated base at rate 1-to-1, weak acid and strong base at 2-to-1, and weak base and strong acid at 2-to-1 ratio. And through the calculations, through the mathematics, we proved that starting with the base, that in order to have a buffer solution that resists the change of the pH, we have to have a weak acid and its conjugated base in a ratio 1-to-1. We proved that even when we have a weak acid and a strong base, or a weak base and a strong acid at a ratio 2-to-1, still we will be able to form a buffer solution. So now we will see how can we calculate the pH of a buffer solution, okay? How can we calculate the pH of the buffer solution, which is known as the Henderson-Hasselbalch formula, okay? Now, we know this is, as I said, this is not part of the outcome, but I will explain it to you so you know the background, and then you are implementing the formula into everything that we will do. And you will see examples that we will do when we go to titration, and everything will make sense with this explanation. So Henderson-Hasselbalch is saying that the pH of a buffer solution is calculated as pKa, I will explain what is it, plus log concentration of A minus in aqua solution and concentration of the weak acid in the aqua solution. Let's see, how did they figure that out? So we know that Ka, based on a very general HA plus water will give us H plus and so on. We can figure out that the Ka expression will be the hydronium or proton, the concentration, times A minus over the concentration of HA. Agree with this? Yes. Now, what do? Is we log both sides. So this is something math. Log with base 10 of Ka is equal to the log of this expression here. Concentration of proton times concentration of conjugated base over the concentration of the weak acid. Now this part here, it's not even going to be asked you at all, but I'm showing you why do we have this formula, okay? Based on the laws of logarithms, that is saying that log of A over B is equal to log of A minus log of B. What I am doing, I'm rewriting this expression as log of concentration of hydronium times concentration of A minus over concentration of the weak acid. And then applying the quotient law of logs, this is how it is known. We can have that we have log of H plus minus, no, plus log of, because when we are multiplying, log of A times B is equal to log A plus log B. Then we'll have log of the concentration of A minus over the concentration of the weak acid. Okay, so now on one side we have log of Ka is equal to log of concentration of hydronium plus log of concentration of conjugated base over the concentration of the weak acid, just by logging both sides and applying the log's law. Now, what is the log of H plus? Isn't log of H plus the pH? Yeah, pH. And now, when we see that we are logging concentration of either H plus or the OH minus, we are just adding a P there. And for the sake of saving the same quote unquote way of presenting, we will call this pKa, but it is nothing but log of the Ka value. So now if we rearrange it, we will have the pH is equal to pKa, which will be with so you bring that here on this side, and then you bring that, because you bring that here on that side, will be a negative. So bring that on this pH on the left and pKa on the right, and then you will have that pH is equal to pKa plus log of the concentration of A over the concentration of HA. This formula is not on your data booklet one, because, as I said, it's not quite part of the curriculum. They are asking you to find to calculate the pH of the buffer session using the ice table, but this is a shortcut. Okay, this is a shortcut. This formula is used to calculate the pH at buffer. Why do we need this? We need this to identify if the solution is a buffer or not. What we will do as the first step is we will calculate kPa, and then anything that is between plus minus 1 of the kPa, it is still considered a buffer solution. What am I saying here? Let's suppose that I'm just taking some of the buffer or the weak acids. So HF, CH3COOH, carbonic, and H3PO4. From the data booklet, what we are able to find is the Ka value. So now open your data booklet and find what is the Ka value for those given weak acids that I'm stating here. So when we have one hydrogen to be able to release in those weak acids, then we will have a 1 Ka value. But on the cases when we are dealing with polypropic entities, like in carbonate, hydrogen carbonate, and phosphoric acid, then we will have more than 1 Ka value. And now let's calculate pKa, which is nothing but negative log of Ka. So now in your calculator, figure out what is the negative log of each of those Kas. And I have them here as 3.2 for the first one, 4.8 for the second one, and then the third one has 2, so one is 6.4 and the other one is 10.8. And then on the third one we have 3, which are 2.1 for the first one, 7.2 for the second one, and 12.4 for the third one. A buffer solution that are dealing with those entities is any solution that has a pH plus or minus the pKa. So a buffer solution will be any solution that has those weak acids with their conjugated base in any situation that we said that they can be formed. Weak acid conjugated base, weak acid strong base at a ratio 2 to 1, weak base strong acid at a ratio 2 to 1, that have a pH of plus minus 1 of 3.2, meaning that will be anything that is with HF and F minus that is ending up to have a pH of 2.2 to 4.2, it's considered to be a buffer of this HF and F minus, or plus minus 1 for the second one will be something that is anything that is ending up 3.8 up to 5.8. And here when we have 2, we'll have one that is going from 5.4 to 7.4, and the second one will be 9.8 to 11.8. And on the third one, we will have 3, but the most common one is the second one, because it is even close to the pH of our blood. That is, it has to be on the range 7.1 to 7.4. Let's see an example in which we are using Henderson-Hasselbalch, which is this formula, pH is equal to pKa plus the concentration of A over HA. When we are dealing with the defining if it is a buffer, yes or no, if the solution that we are forming is a buffer solution, yes or no. So let's suppose that we have this example here in which we have a concentration of 0.10 moles per liter of CH3COOH added to 0.080 moles per liter of CH3COONA, knowing that the Ka value for this acid is 1.76 times 10 to the power of negative 5. So we are calculating the pH and then asking, is it a buffer? Is it a buffer or not? Or not? Is this solution a buffer or not? Okay, so the very first step will be, we'll calculate the pKa. Step 1, let's see, step 1, because there are only 2 steps here, honestly. Step 1 is, let's calculate pKa as a negative log of Ka, or negative log of 1.76 times 10 to the power of negative 5. Enter this in your calculator And do not forget to use brackets because the calculators need that guide. I have 4.75. So what do we have to keep in mind here is that it is a buffer if the pH of this solution is between 3.75 and 5.75. This will make it a buffer solution. Good. Step 2 now, using the Henderson and Hasselbalch formula, let's calculate the pH of the solution using Henderson and Hasselbalch formula. Okay? So the pH will be pKa plus log of the concentration of A minus over the concentration of weak acid. So we know what is pKa because we calculated it in the first step. So will be 4.75 plus log of, see what do we have now as a given? The concentration of the base. What is giving us the concentration of the base? 0.10 or 0.080? The base is 0.080. This is the conjugated base. Okay? So we'll have 0.080 moles per liter over the acid. The concentration of the acid is given to be 0.10. So 0.10 moles per liter. Then the pH of this solution will be, I have it as 4.65. Is this 4.65 within the range of 3.75 and 5.75? Yes. Then this combination of the 0.10 moles of CH3COOH and 0.08 of CH3COO and A is great. It's good to be considered a buffer solution because we have the situation of a weak acid and its conjugated base. See, calculate the pH and then see how we are working with it. So what will be, a question is like this, what will be the pH of a solution if 5 milliliters of 0.1, 0.10, let's say, moles per liter of hydrochloric acid are added to, we are going now to a bit a titration, but still staying at buffer, okay, buffer area. Added to 100 milliliters of 0.10 moles per liter buffer solution. So let's see now why even adding some strong acid in a buffer solution of CH3COOH and CH3COO minus. But this is the combination of the buffer solution. So let's see now why, how is it resisting? How is it still resisting the pH? Remember what we said, buffer is all about resisting the change of the pH, okay? Meaning that will be at a certain small range. Remember what we said yesterday when we were explaining the pH curve that we have, that area that the pH is not changing that much when you are starting to add uh, any strong base or any acid or any base into the solution. Okay, so that buffer area, now we'll see why it is not changing it. And then we will do the shortcut for that. So what we have here is conjugated base. Why conjugated base? Because we are adding acid. So since we are adding acid, then the acid that we are adding will react with the base, because we are dealing with acids and bases here. So the conjugated base, CH3COO minus in aqueous solution, is reacting with hydrochloric acid. And since this is a strong acid, will go to completion, is not an equilibrium reaction, to form CH3COOH in aqueous solution. They are all in aqueous solution, plus Cl minus. Are we good with the reaction here? So now let's mimic now the ice table, okay? In terms of moles, as we did in the previous examples. So what is the number of moles for CH3COO minus? Now, the number of moles will be calculated based on the fact that we have, the previous buffer, whatever we were using here. It's not this concentration of the buffer, but it is the previous one that we were using. So this is acid was 0.10 moles per liter. We said that it is a buffer, huh? The example that we did before. And this is 0.08 moles per liter. Let me verify that. Yeah, 0.08 moles per liter and 0.10 moles per liter. Good. Okay. So now, in 100 milliliters of this buffer of previous, I will say here, previous buffer solution. Okay. So now, in 100 milliliters, how many moles of the conjugated base do we have? How many moles of the conjugated base do? So 0.08 moles per of the conjugated base per 1 liter times 0.100 or 0.0, yeah, 0.01 liter, 100 milliliters is 0.1 liter. So liters per liters are canceled out, and then we will have 0.008 moles of the conjugated base. And when we are calculating the moles of the weak acid, then we'll go 0.10 moles of the weak acid per liter times 0.0100 liters. I might know this is not over 1 will be 0.01 moles of the weak acid. Okay, so what we are finding here is the number of moles. Okay, so initially what we have, since we have this buffer solution at those specific concentration, in terms of the number of moles, well, what we will have is 0.08 moles of the conjugated base. We are adding 50 milliliters at a concentration of 0.10 moles. That means that we will have 0.0005 moles of the strong acid. And then what we have on the product in terms of moles is 0.010 moles of the weak acid. And of course that we have some chloride ions, but it is irrelevant because it does not affect pH. pH is affected only by the concentration of hydronium or protons and the concentration of hydroxide. Makes sense because there are a lot of zeros here and I was good. So now the change. Which one is the limiting region here? Is hydrochloric acid or the conjugated base? It's the hydrochloric acid, okay? Meaning that this all will be used up. So we are using 0.0005 moles of the hydrochloric acid. Since it is 1-to-1 ratio, the same amount will be used of moles will be used for the conjugated base. Now that we are changing the side, we will have a change of a positive change of the same number of moles because we have this ratios 1-to-1, 0.005 moles. So at the equilibrium, what we have is, I will write it in a weird way so that you can see it. First of all, this hydrochloric acid was all used up. And what do we have for the conjugated base is 0.008 minus 0.00 and another 0.5. This is the number of moles that we have for the conjugated base. And for the acid, the weak acid, will have 0.010 plus 0.0005 moles. Now, those number of moles are in one volume, the same number, the same volume, okay? So when we are calculating the concentration of each of them, we have to consider the volume that we are working with. But when we have ratio of the two concentration, then the ratio of the concentration A over the concentration of the acid is the same as the ratio of the number of moles. Okay, so number of moles for the conjugated base or for A minus over the number of the weak acid or HA. So when we are working with the ratio, the ratios of the concentration is the same as the ratio of the moles. This is why we don't have to actually find the concentration when we are using the Henderson and Hasselbalch formula, because we are dealing with the ratio. But if you feel that no, I need to find the concentration, then take this number and divide it by the volume. So, and take this number and divide it by the volume. And the volume will be whatever was originally, that was 100 plus whatever you are adding. So 100 plus 50 milliliters. And then this will be again 100 plus 50 milliliters. But as I said, like even in terms of the units, you will have moles per liter divides by moles per liter, and this is moles of the conjugated base and moles of the weak acid. Then liters and liters will cancel out, and then you will end up the same as moles of conjugated base over the moles of the weak acid. So since we are dealing with the ratio, we do not go through the step of calculating the concentration when we are using Anderson and Hasselbalch formula. Does it make sense, guys? So now when we are calculating the pH of this solution after this acid is added, then using the Henderson and Hasselbalch's formula, we'll have pKa plus logs. This is the formula, logs of the concentration of A over the logs of the concentration of the weak acid. But we are going to, since it is a ratio, we are going to not go through the hassle of calculating the concentration, but just finding the log of the number of the weak acid, or sorry, the conjugated base over the number of moles for the weak acid. Okay, that in our case is pKa was 4.75, is it right? From the previous example. So 4.75 plus logs of, we have those ratios now, 0.008 minus 0.0005. We are adding the acid, and 0.01 plus 0.005. So the concentration of the acid is increased, okay? The concentration of the acid is increased because you are adding acid. And the concentration of the conjugated base is decreased. So now the pH will be 4.75 plus a log of, someone had those numbers, 0.0075 and 0.0105, and will be, I have a 4.60. And since this is still within the range of 4 plus 4.75, that is the pKa of this acid, plus minus 1. So still is on the range 3.75 to 5.75, this number here. This is why still is resisting the change of the pH, okay? Even though that we are adding a strong acid with a pretty high molarity or concentration and in an amount of 50 milliliters. This is for the buffer. So you know now what is a buffer, resisting the pH. You know now how the buffer is formed, and you know how to calculate the pH of buffer without going through the ice table, but using the shortcut that is the Henderson and Hasselbalch formula.